Welcome to the Foundry by Forge College. Let's get right to it. Hitting send and just hoping it works? Yeah, that's not exactly a bulletproof engineering strategy, right? In today's explainer, we're looking at the types and life cycle of Ether transfers. We're going to literally unroll the blueprints to demystify how Ether actually moves on the blockchain. Let's break this whole journey down.
Now, I know you might have a bit of mental whiplash coming straight from our last lesson on the Solana mainnet versus DevNet environment. Well, stretch your neck because we're pivoting back to the wild, unpredictable world of Ethereum mempools. Different architecture, completely different rulebook. Let's reset and track some state changes.
Here is today's master schematic. 1. Welcome to Ether transfers. 2. 3 types of transfers. 3. The transaction assembly line. 4. Mempool and execution checks. 5. Tracing gas and finality. And 6. Next steps and debugging.
Section 1. Welcome to Ether transfers, preparing for inspection.
To really inspect these checkpoints, we got to know exactly what we're looking at. Every single journey here begins with an externally owned account, or EOA. It's basically the person walking onto our factory floor to start the assembly line. Controlled by your private keys, it's the absolute origin point, the initial spark that broadcasts a raw, signed transaction out to all the network peers.
Section 2. 3 types of transfers, the machines we built.
If you just assume every transaction behaves exactly the same way, you're going to miss some absolutely crucial details. At an implementation level, we're actually dealing with 3 specific machines here: value transfers, contract invocations, and contract creations. You can think of these as handing cash directly to a buddy, putting coins into a vending machine to trigger some mechanical logic, or literally building a brand new vending machine from scratch. The value transfer is, by far, our simplest schematic. You're sending a non-zero value, totally empty data, directly to another EOA. It's the canonical send Ether operation. It just atomically subtracts from your balance and adds to the recipient's without running any complex code. It's clean, simple, and highly predictable.
But a contract invocation? That sends Ether along with instructions. You're filling out that data field with a function selector and encoded arguments. So that Ether might be stored, it might be forwarded, or, if the code is buggy, it might be locked away forever. You aren't just moving money here. You're essentially hitting play on a piece of software.
And that brilliantly illustrates our third type, contract creation. This one is super unique because the destination, the to address, is literally null, empty. You're sending initialization bytecode out into the void to birth a completely new contract. And you can even attach an initial Ether balance right in inception. Pretty cool, right?
Section 3, the transaction assembly line, tracking the journey.
So let's take those 3 transfer types and place them onto our assembly line. Every single transaction has to survive this chronological gauntlet. It goes from the initial broadcast at 0 seconds, to resting in the mempool, to execution and block inclusion, right up to reaching absolute finality through network confirmations.
Take a close look at this master blueprint. This table is your conceptual backbone for exactly what to observe at each checkpoint. Notice how a basic value transfer is just an atomic balance update, right? But a contract invocation during execution requires you to actually dig into the logs and internal transactions to see if the contract forwarded your funds or if it panicked, reverted the whole process, and gave you absolutely nothing back.
Section 4. Mempool and execution checks, passing the test.
That gap between broadcasting and block inclusion, that's where the magic, and honestly, the frustration happens. The mempool is our factory's quality assurance gatekeeper. It does a quick, light sanity check, verifying your cryptographic signature, ensuring your nonce is in order, checking the gas limit, and making sure you actually have the balance to pay for it all.
Now, while a node can easily verify if you have enough balance for a simple value transfer just by doing basic math, a contract invocation is wildly unpredictable. Why? Because its exact gas cost isn't truly known until it actually executes. The mempool will accept it if your balance looks somewhat sufficient, but there's this massive cloud of uncertainty hanging over it until it officially hits the execution block.
To put that into perspective, see you send 1 ETH in a basic transfer. The state transition happens atomically in the block. 1 step, done. But with a contract call, that same 1 ETH could trigger a massive chain reaction of internal transfers. The mempool has no idea. The contract could route it, lock it, or completely fail and revert everything post-inclusion.
Section 5. Tracing gas and finality, settling the bill. Okay, once a block is finally executed, we have to figure out who actually paid for the mechanical work. Listen closely, because this is a massive trap for beginners. The origin EOA always pays the gas, always. Ether loss to fees is never deducted from a contract's balance. Even if a smart contract ends up routing money to 5 different people, the person who initially hit send on the EOA is footing the entire bill. No way around it.
And remember, blockchains can reorganize. Mempool acceptance absolutely does not equal execution success. You have to check your confirmation milestones to know your funds are actually safe. Waiting for 1, 3, or sometimes even 12 confirmations ensures that the block your transaction is in doesn't just suddenly get dropped because of a chain reorg.
Section 6. Next steps and debugging. Your action plan.
Referencing these schematics is going to become second nature when you're debugging. It's what separates just guessing from actual systematic engineering. So to quickly recap our factory orientation, always classify your transfers. Never ever trust the mempool until you check the receipt and the logs. And always remember, the origin EOA pays the gas bill.
In our next explainer, you're going to put on your hard hat and produce a local transaction demo artifact using everything we just went over today. We'll spin up a local node and watch these concepts play out in real time right on your screen.
So, are you ready to fire up that local node and trace your first smart contract execution? Well, before you do, I want to leave you with a thought. If the mempool is just this giant public waiting room where absolutely anyone can see your intended logic before it actually executes, how secure is a transaction before it's securely mined into a block? Really think about that. To learn more about this subject and explore our other Web3 topics, head over to forge.college and keep building. Thanks for joining me on this explainer, and I'll catch you in the next one.